Dear students, you might have already seen my video on linear regression and polynomial regression, and I hope you have understood the basic idea of regression, linear regression, and polynomial regression. In this video, I am going to help you understand it better and give you an ocular proof how linear regression and polynomial regression converges to a solution using gradient descent algorithm. So this is small software demo that I have made, and I guess and I hope that it will help you understand the concept better. So let me run. So on the left side, this graph shows the data set that I have inputted in the system. So let me first upload the data set. So this is the data set we are going to use for this exercise or for this demo. And as it can be observed that this data is not linear. So when we use linear regression, as might you have understood, that tries to fit a straight line to the data. And this data distribution is very different from a straight line. So first, let me run linear regression and see what happens. So this is how it goes. On the right side is the error. So system is trying to reduce the error using gradient descent optimization method. And these are the hypotheses that system is learning to fit the data. Uh, Let me just write it. So it is trying to fit a straight line. And we can write this hypothesis like this. I am writing in terms of theta. It is just an equation of straight line. So that is theta 1 not. So all of these lines belong to this hypothesis. So system try to minimize sum of square error, and this is the best it can do. Right now, I have run the system for 40 epochs or 40 iterations. You can increase the iterations to see, but you can see that the data is not linear, and we are trying to fit a linear line. So it's actually we are getting high training error or high bias. Okay, now we can see that this is, if we use polynomial regression, probably system will learn it better. So first, now uh, let me run the system using polynomial regression. Okay, now polynomial regression, this is second degree polynomial regression, or it's a quadratic function. So it's kind of a hyperbola, and we are fitting second degree polynomial, and we can see that now we are learning the data much better than a straight line. And just to remind you again, this hypothesis is of the class, let's say, h of theta. So we have added one more feature. So it's this plus theta 2. And I have added squared or polynomial features in the data. So this polynomial regression is of second degree, and I have added second degree features. So these are just x squared. So I have used x squared here. So now this is the form of polynomial regression that I have run here. And we can see that now our error is quite less. You can just go back in the video and can see that for linear regression, the error was around 110 or 20. And now the error is reduced to 76.92. One more thing that I have covered in the lectures is that once you add polynomial feature, the problem of normalizing the feature is very important, because I have squared the features. So the features are in very different range. So I have, let me clear the screen. I have, I will run this demo another time, but this time it's a polynomial regression, but with normalized features. So all the features are between 0 and 1. X and x squared both are normalized to have the value between 0 and 1. And let's see what happens. So now this is how it goes. Visually, it is a bit different from polynomial regression, but you can see that error that we are getting is quite less as compared to our previous iteration, or the previous when we learned polynomial regression. Now the error is only 16.01 after 40 epochs. So it means it's polynomial regression. Hypothesis is same, but all the features are normalized. So this also shows that when you use polynomial regression, it is very important to have normalized feature because the ranges are very different. This is only example for second degree. Let's say if I add third degree or fourth degree features, their scales would be very different. And for gradient descent method, it will become very difficult to optimize that cost function or sum of squared function. So hopefully this demo has given you more confidence that what we have learned actually works in a real life and how it optimizes. So if you have any query, again, you can post it in the video under the video in the comment section, and I will try to answer. So thank you very much once again.